For lesson 2.8, we are finally going to figure out the slope of a curve. Specifically for this lesson, just the slope of x squared, and then we're going to try to use our findings to sort of expand the concept outward and see if we can figure out the slopes of other curves. This is the other kind of half important part of Unit 2, so if we can figure this out, we've really got the whole idea of what we're looking for down here. So let's go. In our last lesson, we actually answered the first half of our problem and how we can figure out the slope of a curve, which is how can we figure out an accurate slope for any of the infinite points that are on the graph of the curve. We knew that we weren't able to use the slope formula on a single point because that would give us an undefined answer. But what we figured out is that if we took the slope of the point we wanted between that and just another really, really close point, we were able to reasonably figure out what the slope should be using a limit statement. In my example problem, I had the equation 3/4 x squared, or when we approached the x value of 3, the slope value from both sides of the graph started to narrow down towards 4.5. Therefore, we were able to reasonably conclude that this is the true limit of the slope and thus the slope of the tangent line. We also figured out that if you tried to take the slope between a point that was so much as 1 away from what we were looking for, our answers weren't very accurate. When we took the slope between 3 and 4, we got 5.25, which is a pretty big overestimation from 4.5. The slope from 3 to 2 gave us 3.75, which is a pretty big underestimation. It is worth noting, though, that if you were to actually take an average of these two slope values by adding them up and then dividing by 2, the answer that you would end up getting is the same 4.5 that we found for the limit here. 5 plus 3 is 8, and 0.25 plus 0.75 is another 1, so this is 9 divided by 2. The same thing will happen if you actually take any of these two slopes from the different sides of the function that are equidistant from each other and taking an average. You'll always end up getting 4.5. This is important because it means that there is still some value for taking a slope that might be 1 away from the point that we're trying to find the slope for. Even if the initial answer isn't accurate, we could maybe find that same slope from both directions and take an average of those things, and we could probably get to our conclusion a lot quicker than needing to deal with little decimal points and very strange y values. So the first problem on our assignment gives us the equation of x squared, and for each point on the table here, we want to find our y value and the slope from that point to either the next point below it or the next point above it, basically the point that either comes after it or before it. We'll record our slopes in the third column of the table just like we did in our last assignment. When it comes to finding the slopes, the convenience of taking these points that are 1 away as opposed to something closer like a decimal is that if we are putting these points into our slope formula of y2 minus y1 divided by x2 minus x1, the difference between these points is always going to give you a denominator of -1, meaning that if we really want to find the slope between 2 points on this, all we need to do is subtract their y values and then just switch the sign of our answer. The other convenience of using all whole numbers here is that it's really easy to get the y values. We probably wouldn't even need to use a computer for this at all. We just need to square all of these things. 4 squared is 16, 3 squared is 9, 2 squared is 4, so on and so forth. Don't forget that these should all be positive values as well because everything squares to a positive. So if we want our first slope for -4, we need to do a subtraction of the y values between the y value here and then the one that's below it, and then we need to divide our answer by -1, which means we just need to switch its sign. So 16 minus 9 is 7, and we're going to switch that to a -7. 9 minus 4 then is 5, so this is negative here. 4 minus 1 is 3. 1 minus 0 is 1. And now, because we're switching the direction we're moving, 0 minus 1 is -1, but this is going to turn positive. 1 minus 4 would be -3, -5, and -7. We actually can't technically get the slope of the next point because we don't have the next value on our table. We could reasonably figure out what it is, but I don't think it matters. We probably have enough points here to get the pattern going. Moving over to the second table here, we're going to try to take the slopes by subtracting everything from the y value that's behind it. And because our x values are now moving in the reverse direction, -3 minus a -4 is going to give us a +1, and that's going to hold true for all of the changes in x. So we don't need to switch any signs this time. 9 minus 16 is -7. 4 minus 9 is -5. 1 minus 4 is -3. -1. 1 minus 0 is 1. 4 minus 1 is 3, 5, and another 7. We also can't get this first box because just like over here, we don't have the x value that comes before this, although we could get it. When I look at the patterns of these two tables, I'm noticing that they have pretty much the same y values and they're in the exact same order. They are a little bit off because of the way that we took the slopes, but that, of course, is probably just due to the overestimation and underestimation that we take depending on the direction that we were using our slopes. This means that we could probably turn this list into like a true list of slopes by averaging everything out. But first, let's see if we could just find any sort of pattern in these things. I mean, the numbers are progressing in a simple enough manner that we probably could figure out a function that would represent all of these slope values as y values to go with these x's. Maybe we can put these into Desmos in some tables and see if we can visualize what it would look like if we had a graph where these were our x values and instead of these being our y values, the slopes were our y values. So here are our x value inputs, here's the y values that we got out as answers, and here are our over and under estimations. We can also see, thanks to this table here, that we can actually get these two missing things, which were a -9 and a +9. When we look at the way the points connect from the tables on the graph here, we can see that we're just looking at a linear equation, and both of them seem to be parallel lines, which means that they have the same slope. We can even see pretty clearly what that slope is. Both of them are moving up to and over 1 for a slope of 2. The only difference between the two things that we have is that this one has a y-intercept of +1 and this one has a y-intercept of -1. So we have our overestimated slope equation from our x plus 1 table, which is 2x plus 1, and we have our underestimate from this table, which is 2x minus 1. Again, what we figured out in our previous lesson is that we could get any of these slopes here to be the accurate slope at any of these points by taking an average of the two things we found, adding them up and dividing by 2. So I bet we could probably do the same thing with these two functions here. So combining the two functions in the numerator of our fraction, we have 2x plus 1 plus 2x minus 1. That means that our plus 1 and minus 1 are going to cancel out, leaving just the two x's here that are going to combine to make 4x divided by 2, which ultimately simplifies to just 2x. Now we have finally reached the answer to our question of how could we efficiently define the infinite slopes of a curve. The answer is the same way that we define the infinite amount of any sort of numbers that are being generated from something. That's a function. A function is how we have a pattern of infinite numbers, and since we have infinite slopes, the slope of a curve is a function. Slope functions are so important that they have special names in calculus. We call this the derivative. And whenever you put an x value into this equation, the y value that it gives you as an answer is actually also the slope of x squared at the same value you put in. We can even prove this to ourselves by taking an average of a couple of these slopes here and then putting that same number into this to test our theory. For instance, if we look at the two slopes that we got for -2, that is -3 and -5, those add up to give us -8, which divided by 2 gives us -4. So the slope at x squared at -2 is -4. If you put -2 into this derivative equation, 2 times -2 gives you -4. Over here for +3, 7 plus 5 is 12, and 12 divided by 2 is 6. 2 times 3 is 6. Now you can basically generate as many slopes for x squared as you want very quickly by just putting them into the equation 2x. This is an extremely important conclusion to reach, and we're going to work with it a little more on the assignment. I believe there's two other sets of tables where we're going to try to repeat this same method and see if we can get some slope equations that maybe are different from 2x. Are there any transformations on x squared that can change the way the derivative shows up? After all, we don't know if this is any sort of pattern in the derivative or this is something completely unique to x squared and everything else could be totally different. But that's what we'll figure out next time. That's all. See you soon.